All right. Well then, welcome back to the last day of our tutorial. It's been a great week. Thanks for sticking with us for all this time. Today we'll have the last session, and we also have a few questions for you about how we ran this tutorial and what your experience was. We'll do that in one of the breaks. But until then, today, Menno Fraters will talk about how to build complex model scenarios. And I'll just hand it over to you, Menno.
All right, thank you. So this should be it. So I hope you now see my screen over here with the slide. So today, I'm going to talk about a project which combined with Aspect can allow you to build more complicated models easily. And that project is called the Geodynamic World Builder. So what I hope to answer in this presentation or in this part of the tutorial, it will be interactive, don't worry, is, well, what is a Geodynamic World Builder? Let's start out with that. How can you use it in Aspect? How would you actually make a complex model or simple if you really want to model with the World Builder? And where can you find more information? And as a last note, what are development plans and how can you contribute? Okay, so let's start out with what the World Builder is and what the basic idea behind it is. Why is it needed? And to get an idea why it's helpful and for what situations it's helpful, let's take a step back and think about what kind of models there are in generic models. And very broadly, you can simplify it into three different types of models. You have the very simple synthetic models. Think, for example, as of the elastic beam. And I'm not talking about the physics, which is complicated, but I'm talking about the setup. It was just a box in a box, basically, a rectangle in a box. And you can easily use the parameter function to set it up. So these simple static models are easy to make and good for simplified problems and benchmarks. Then you have the data-driven models, and these models are, you can think of loading in tomography data for part of the Earth, and then maybe modifying in that a little bit to get temperature and some kind of composition out there, and you can get very detailed states of how the world currently is, or what's an estimate of what the world currently looks like inside. And you can do that by just loading in ASCII data, doing some operations on it. And there is quite some functionality in Aspects already to do something like that. And these are actually very good for example, steady state models. If you, for example, want to load the data of a part of the Earth and just run it and see how the flow would look like, this is perfect to do it like that. And then you have this third group of models, which are complex synthetic models. And these models are, well, for example, you want to say, well, I have several hypotheses of how this region looked 10 million or 20 million or even 14 million years ago. And I want to figure out how that initial state would influence the evolution, and how do I get from the past to maybe the present. And or you just want to investigate these complex static models. For example, you want to investigate a 3D subduction setting, and you're not interested in a specific case, but more complicated, just a complicated general case. And so this is the third case where you have these complex synthetic models. And these are quite hard to make, as I found out myself. But they're really good for evolutionary modeling. And this is just a broad generalization. Doesn't mean that you can't use ASCII data for evolutionary modeling or any other way around. This is just a very broad generalization. But the point I want to make is that the world builder is designed for this third case. And you can actually do the first case with them without the problem. And you may in the future even be able to load in ASCII data into the world builder and couple everything, but that's currently not the case. But it's designed for this third case. And it's designed to make it a lot easier. And just to get you a feeling of what I mean, that it becomes really complicated really quickly. This was something I did in aspects, I think about 6 years ago now. And it's just a simple 2D subduction case. So we have a sticky air layer over here. We have two crust compositions, the orange one and the yellow one, and we have a mantle composition. And I'm not going to explain in detail why this would be a good setup for a subduction case, but the only complicated things here is that there's a little curve in here, so that there's a little bit more orange crust here, subduction plate crust here, and there's a little cutoff. And to be able to do this in aspect, and back then it didn't have some of the fancy function parser features yet, I had to write this. And I won't go into detailed explanation. So nowadays, if you would want to write this in the function parser, you would probably cut it up into several lines. It wasn't available then. But even better, you would probably just go ahead and make a separate plugin, which I ended up doing. But even then, you can see these are complicated problems, and they're hard to debug. And even for me, especially in this case, I had to unwind it every time I wanted to change something, add a new feature, for example. And that was quite difficult. So I hope at least and this was just 2D. So I hope the case that these initial conditions for these models have at least one of these problems, that they're, well, not readable, and even for the developers of that initial condition, they're hard to modify, they're not really extendable, and the portability, for example, to other codes, is also quite hard. You basically have to go and reinvent the wheel every time, which I think is a waste of effort. So the goal of the Geodynamic World Builder, or in short, World Builder, is just to solve these problems. And it does that by just going back to the basics. And it divides up it in a specific coding philosophy to solve these extendability, portability, and shareability issues, so that you can easily share it between different codes in different languages, etc. And it also has a specific user philosophy, which aims to solve the readability and modifiability issues. So I won't go over this in too much detail, but important one is that it uses a single text-based input file, similar to Aspect. The format is a little bit different, but you just need a single input file to modify or to create the initial conditions generated by the world builder. And it basically supports all the major operating systems. It has interfaces to different languages, so that it can be implemented in different codes. And it's actually, besides Aspect, it's also implemented into other codes, which are actually Fortran codes. And it's another thing to point out here is that it's safe to use in parallel codes, which is important in Aspect. Oh yes, and there is a very strict version numbering to ensure that the results are reproducible. And we'll go into that a little bit in detail later on. But it's very strict on version numbering, and you actually need to supply the version number you made the input file for to make sure that it remains reproducible. then the user philosophy. And we'll go to this in a lot more detail later on, but I just want to give you a quick overview. And the idea is that we have this very complex Earth, but we need to somehow generalize it, and we want to parameterize it. And the idea is that you look from above and divide up basically the surface into lines and areas. And these lines and areas can implicitly define a volume. And I will talk to that later more how that actually works. In each volume, once you have that volume, you can actually assign some kind of temperature or composition, and in the future actually also other things, to define the initial conditions of the world, basically. And this all needs to be parameterized in a way which is human readable. And for that, the JSON file language was chosen. It's not important for you, it's just if you want to have some reference of what kind of language it is, it's JSON. But we'll go through it step by step how to actually make an input file. Okay, so this was a very high level overview. Let's dive in a little bit more. This is not going to be in too much detail yet. We'll go step by step later on, but for now, I just want to get you the general idea of how to work step by step. So say, for example, we have this map view of the Caribbean plate. So here we have the North American plate, South American plate, and the Caribbean plate. And we're going to ignore most of it, but we're just going to be interested in this box over here. And we're going to try to make this subduction zone as an initial condition. And how you would start out is, well, first draw the box. And in this case, we define 7 different points. So 1, 2, 3, 4, 5, 6, and 7. And you start by dividing it up in several areas. So here we have the green area, which is defined by point 1, 2, 6, 5, and 7, which is basically the Caribbean plate. Then we have this area, which is the South American plate, defined by point 2, 3, 4, 5, and 6. So these are the area features we will talk about later. And then we have a line over here. And this line is trench, the subducting plate, which is defined by points 2, 6, and 5. And now we're going, so this is the same box. Now we're going to have this 3D rendering of it, and how the world builder would, in the world builder it would go step by step in actually making a model. And let's just start by filling the box, which is currently empty, just with the Menno material, just for convenience sake. And we'll make that red. So you actually have to do this. There's actually a background, but let's just fill it with a background Menno material. And the second thing you would do is, well, let's do the Caribbean plate. We define the points on the surface and we give it a certain depth, and that defines a volume. And then in this volume, we can go and attach temperature and composition models. But I will go into that later. We can do the same for this Atlantic plate, the South American plate. We have specified the surface area and we give it a certain depth, and that's the Atlantic plate. And then we only are left with the subduction zone, which is a line feature. So we create a line over here, and what we actually can do is that line, we can specify a certain angle in which basically defines a plane, and the angle, and it needs to go in some kind of direction. For this, we let it go dip into this direction. And we also defined a certain thickness, and with that thickness, you again have defined a volume. And that looks like something like this. So that's the general idea of how the procedure goes. And this is just a spoiler of what we'll actually end up making. And that's defined by this file. Don't worry, I will show that picture in more detail later. I will explain the picture. It was sort of a teaser. So for this part, again, I won't go into too much detail. I just want to get you to first to get the general concepts. One thing I want to point out is that for every WebBuilder file, you have to specify a version number. And in this case, Aspect uses by default version 0.3. So in this presentation, we're going to use version 0.3 and define it over here. Second is that there are these tectonic features, which is sort of features, and these are in a list. And this is how you in JSON set a list. This is what the angles bracket. And in this list, we are going to define several objects. And these objects, they start with the curly bracelet and end with the curly bracelet. And each of these objects, these are feature objects, contain information. And information contains, among other things, what model we're actually going to use. In this case, we started out with the mental layer, just want to fill the whole thing. We give it a name, and a name is just for you, for readability purposes, and we give it coordinates. So where is this feature? And this is the minimum all the features actually need. You need a model name, or name, a name, and the coordinates. We do the same for the oceanic plates, and again, I won't go into detail. We call this now the overriding plates because we're actually going to divert a little bit from reality to make it a little bit more interesting. And so we define this, now at the surface, we define two oceanic plates. And then we have, so these are all area features. We define the coordinates here, define an area. And now we have a first line feature. And that line feature is subducting plates. So the model here is subducting plate, and we give it a name slab. It doesn't really matter what you name it. But it's important that you just give it a name for you to make sure that you know what it is. And again, we give it coordinates, but the coordinates, we give it 3 coordinates. So coordinate 1, coordinate 2, and coordinate 3. And note these coordinates are in 2D because we're looking from above, from the map view, and we give the coordinates, and these define a line. And so there are some special things which is line features. For example, I said you have to, it has to dip in some direction, and we'll do that with a dip point, which I explain in more detail later. And you need to say how long is this this slab? How thick is it? What's the angle? And you can also, well, we'll go into this a bit more detail later, but you can define different compositional models and different temperature models to these kinds of features. And well, this is just to give you a preview. This is the resulting model of the file you just saw, and this is actually what we're going to build today. Step by step. In 10 steps, so we'll be able to build this model from scratch. And just keep in mind, this is a very simple example. There's much more possible. And just to give you a little preview of what is possible, this is actually one of the models I run with Aspect in my thesis. And this is actually the actual Caribbean example I have. It starts about 20 million years ago. So here we have the North American crust and South American crust, which are the same compositional material. It also goes into the crust of the slab. We have the Caribbean crust over here, which is the more stronger part. And we have some weak zones here to accommodate the prescribed velocity on the sides. So we keep the Caribbean crust on the sides here, and we'll push the rest around it. And this is what the initial temperature model looks like. We can actually just easily change the setup by making, for example, the weak zone a little bit thicker, or creating gaps or weak zones within the slab itself. And this is one of the model outputs where the colors are the viscosity, and the arrows indicate the velocity. And you see that the Caribbean plate is in this case strong. It's It's actually cold and it's strong, strong material, and the oceanic plate, the Atlantic plates are basically moving along it and subducting over here. And so this is not to go into too much detail on this, but if you're interested in the input file for this, it's at the end of the presentation. Okay, so we now hopefully have a general idea of what the world body is and what it's capable for and what it's meant to do. So let's start with what aspect actually needs from the world builder. If you want to use the world builder with aspect, what do you need to do? And there are only two things, well, technically only one thing, but if you want to use it effectively, there are two things you need to do. One is you need to tell the aspect where it can find this world builder file you made. And the second thing you need to do is you need to set it to use the world builder initial conditions as an initial temperature and or initial composition. So that looks like this. We set the world builder file to the location where the world builder file is, and we set either of these to the world builder. And you can actually also, in aspect, you can define multiple initial temperature models, and you can actually just combine the world builder in that. So you can, for example, combine it with an ASCII file if you want to. But this is what's the minimum what is needed. Okay, so what does the world builder need? What do you need to put in that file as a bare minimum? So there are again two things which you need to provide. One thing is the version number. And in this case, the version number is 0.3. And the second thing you need is to define a feature object. And that just looks like this. So in JSON, everything needs to be, in JSON language, everything needs to be contained in one big object, and that's defined by these curly braces. So we need to have these curly braces over here. And then we have several parameters. So this is the version, and so this is a key, and we give it a value of 0.3. Then we specify with a comma that we want to have a new key, and this one is called features, and this features is an array. So this is the very bare minimum you actually need. And so what we're now going to do is try and see if it actually works for everyone. It won't do anything interesting, but let's just see if we can do this. And so make sure you're in this directory. I will go through this on the virtual machine for you as well. And then you can run it with, so make sure you're in session 5, and you can run it with aspect release, and the file name is reference model 1 minimum.prm. So rfm 1 minimum.prm. And then we're gonna load it into ParaView, and we're gonna use one of the files which is available in session 5, which is the full view. And what we're gonna do is, when you load it, it pops up the screen, and we're gonna select search files on the specified directory. And the directory we're gonna set is actually just the name of the input file we had. Okay, so let's now switch to the virtual machine. No share. So you should now be able to see the virtual machine over here. And let's just launch a new window. Let's make it a little bit bigger. So first of all, we're going to go to Aspect Tutorials 2020 and session 5. Okay, I hope we're all there. Let's make it a little bit larger. And now what we can do is we can go one directory back, aspect release.
Menno, can I interrupt you
Yes.
here for a second? Why does this work for you? This will not work for anyone else because there's no aspect release in the directory above session 5.
Okay, I assumed that it was there. So then we will need to make a link. So, okay. So let's see. Aspect minus S. So the question is where is we're going to link to the aspects.
There is an aspect release inside the aspect directory. So if you now do aspect release.
Okay. That's not the case for me then.
Oh, it's not for you. Okay, you can just as well use the release folder that we did on the second day. Oh, but your folder is named differently as well.
Okay.
So for
I messed it up, but please just make a link like this to your aspect release, or just use your aspect release wherever it's located.
Yes, so for everyone else, you can just use the same path you used the last days for starting release models.
Okay. So for me, I will be using this, but yes, please use your aspect release. If that's not possible, you can use your aspect debug. That should be fine. It will just take a slightly bit longer. But most of these models won't be expensive unless we're going to really high resolution, which actually don't need to. So when we run this, you should be seeing this, and it should be done very quickly. If you are encountering a problem with this, let us know in the chat. And Juliana actually posted what for her the command is, which is very similar. Okay. So next thing we're going to do is we're going to open ParaView. Let's open ParaView over here. And we'll add an ampersand to make sure that it's in a separate background process. And so now we're going to here to File, and we're going to load state. And I hope you're in session 5 if you followed along. Otherwise, you can just go to, you probably will be in Home Ubuntu, then you have to go to Aspect Tutorials 2020 Tectonics Modeling Session 5. And in there should now be a folder RFM1 minimal box. We're not going to use it for now, but what we're going to use is this one, PV view full C1t.pvsm. And we're going to click OK. And then there's an option here, and we're going to search. We're going to use the second option, search files on the specified directory. So click on that. It should pop up a data directory. And we're going to click over here on this dot buttons. Let's see, we're going to use RFM minimal box 1. So select that one. And then click OK. And it should load up this. Okay, let's see. Someone is saying RFM file is not found in the mentioned path. Okay, I'm not entirely sure what the question is with RFM files not found.
Could you go over the steps quickly again, or slowly again, how to load the state file and how to change the file paths that are inside the state file?
So I hope the running went okay for everyone. So I will close my ParaView and we'll go over steps again. So I will open ParaView with ParaView and then an ampersand. You can also just open it normally, but this will open it in the directory where we actually need to be. Okay. So we're here, we're in Pair View. We're going to File, Load State, and in Load State, we're going to load this state, which is called PV View Full C1T .pvsm. And we're going to click OK. Then we're going to use the search files on the specified directory, like this. And we're gonna, so that should pull up a data directory bar, and we're gonna click on the dots over here. And then you click on the RFM1 minimal box, and click OK. And then you click OK. And then you should see something like this. And if this doesn't work for you, you can still try, but I will have all the pictures in the slides. I just want to make sure that if you want to view this yourself, so this doesn't show much because there's not much happening, but this is the procedure you have to go through. And so, as you see in the slides, it just looks the same as this. And here are the instructions still. And yes, so if it doesn't work, you can ask in the chat, and maybe the other developers can help. Otherwise, we can go through this in the break. So let's switch back to the presentation. Over here. So we're back at the presentation. So we went from this slide to this slide. So here are still the instructions for if you want to see it. But this what it only shows is this box currently, which is it has a certain temperature and it has a certain composition, and it's not very interesting. So we want to make it a little bit more interesting. But before we go to do that, I want to talk about one optional parameter. And that optional parameter is the coordinate system. And that coordinate system, you can actually use different coordinate systems, but the default is Cartesian. And that's why this just worked. And if you want to specifically have the coordinate system in there, you just define the key coordinate system, and you give the model is called Cartesian. This is already the default, so you don't need to do it, but I think it's good practice to do it. You just show that this model is really built for Cartesian systems. Okay, so next we're going to look at a more generic case of how these individual feature objects, what they look like. And I just want to warn you, I have several red boxes in there. So green boxes, you can just copy the code you want and put them in a world builder file and it will work. But these red boxes, they're meant for illustration purposes, and this can mean that there's, in this case, for example, this one will give an error because there is no feature called feature model 1. But it might also just be a partial file. So just a warning, and it will, and if it's a partial file, it will say in the top. And like I said, this one won't work because there's no model named feature model 1. There's also no temperature model named temperature model 1. Same for composition. But I want to show you this to let you get a general idea of what the different components are of a world builder file, of a feature object in a world builder file. So, like I said, it's an object, so we start and end with the curly braces, and we need to give it a model name. We also need to give it a name to indicate what it represents in the real world. and we need to give it coordinates. And we're allowed to give it a temperature or composition model, but we don't need to. So if no temperature model is attached to it, it won't do anything. It won't return anything in there. It would just, but internally, it will just take the old value and return the same value. So it won't change anything. And if you're interested, later on, you can just go and run this code and see if you can understand the error message. But for now, I just want to continue. And here, the only thing I did was add a second object. And this one is a different object. It has may have different options and may have different kind of temperature models available. And we again give it a different name. And the main thing I want to point out is that what the world builder will do, it will go from top to bottom. It will first process the first feature, and then it will go to the second feature. So if this is in the same location, this feature will be overwritten by this feature. That's a general idea. Okay, and just to go over what now more specifically, what features are available. So like I said, we have two kinds of features currently in the world builder, which are the area features, which means that the coordinates define an area. And these are the continental plates, the oceanic plates, and the mantle layer. And we'll show that what they are a little bit more, but you can also look up in the manual. There's an extensive tutorial in the manual, which I'll give a link to later, on how to actually use all these features and what the options are. Secondly, we have line features. And like I said before, line features are where the coordinates you provide in the world builder file define a line. And these are the splitting plate and the fold. In the future, we may add other area features or line features, or even something called a point feature. For example, if you want to make a volcano, we might add that as a point feature where the coordinate just defines a point, and we'll make the volcano over there. So just to reiterate, area features, for area features, the coordinates parameter defines an area. For line features, the coordinates describe a line. Okay, so what we're now going to do is we're going to start adding an oceanic plate feature. And like I said before, we start with a feature object which starts with it and ends with its curly braces. We give it a model name, which is oceanic plates. So this is similar to a plugin and aspects. There are a certain number of defined models available. We give it a name, and the name again can be anything you want. It's just for you to know what part of the model this is. And then we give it coordinates. So this coordinates is an array of 2D points, so an array of an array. And this defines where this is. And then we'll actually, to make it interesting, because this won't do anything new because there's no temperature model or compositional model attached to it. We actually define a temperature model, which is temperature models and compositional models parameter. And this again is an array of objects. And each of these objects again have a model. In this case, we're going to use the model uniform. And we're going to give it a temperature of 20 degrees Celsius, which is 293 Kelvin. We're going to do the same for the compositional models. We're going to give the model named uniform, and it will just give a uniform temperature of the whole, in the whole feature. And we're going to give that a composition of 0. So these correspond, these numbers in the composition here correspond to what is in the index, as we'll see in a moment. So what we're now going to do is we're going to run aspect release again, but now we're going to use RFM2 overriding plates, the PRM. We're going to again use the same procedure to load the state and so search files in the specified directory, and we're going to use that directory which is generated. So first you run it, and then you can load it. And it will look something like this. So let's go and go to the virtual box. Just to go through the procedure again. So now you should see my virtual. Let's close it down. So what we're going to do is, so for me it's aspect release, but for you use your own aspect release, and we're going to use rfm2.prm. And that should be done quite quickly. Let's see if there are. So for me to, yes, what Juliana said is correct. Okay.
Menno, since you took a quick break at the moment anyway, we had 2 questions that maybe you can quickly address. So one is, could you repeat the git command that updates the repository to add the files? So I know we did that yesterday, but I think not all participants were there at the time, and all of them will not find the files that you use at the moment.
Okay, let's see. So what you do is git pull origin master. Let's make sure that it's on the same line. So this is the command you will use. I will also type it into the chat, origin master. So this is the command you have to use.
Yeah, so if you have not run that yesterday, then please run it now, and that should give you the files in this folder. If you have run it yesterday already and you run it again, it doesn't hurt. So if you're not sure if you ran it, then feel free to just run it again.
Yes.
And the second question is, or did you want to add anything?
No, I was asking
okay.
what the question was.
So the second question is, can we also add 3D topography data inside when we build the model? If we can, what kind of topography data can we use? That may be a bit advanced for this stage of the tutorial. Do you want to postpone that for later?
Sorry, I was just slightly distracted because I see I actually put it in a private message instead of everyone.
Okay.
So git pull origin master. So your question was about initial topography?
Is it possible to add initial 3D topography data in the world builder?
I wanted to talk about that a little bit later.
Currently, okay, then let's postpone it.
Yeah. Short answer is currently only with sticky air, but not with, well, yes. For some, there's a problem with some of the material geometry models and aspects, and the communication with the world builder. But it is possible to do it with sticky air, but it's currently not possible yet to do it with true surface to get real initial topography. That's something actually which I have some ideas of how to do, but I'll talk about it later.
Okay, thank you.
Okay, so I hope everyone has been able to run this example. So now again, we're going to open ParaView. And we'll go to the same procedure. So we're going to File, Load State, and we're going to open RFM2 overriding plate. Oh, sorry, I'm wrong. We're going to open the state, PV view full, and click OK. And then we're going to select the second one, search files in the specified directory. And we're going to use RFM2 overriding plate. And click OK. And click OK. And then you see exactly what I just showed you in the slide. And so the model has become more interesting, but this is actually not what we wanted. This model is 500 kilometers deep. And maybe that this is actually a good time to take a quick look. Leave that at the PRM file for this model. So rvm2.prm.
A quick question: should we follow along, or should we stay in the Power View window?
You don't have to follow along with this. Is the text visible? How to make it
yeah, I think the text is visible.
Okay. Okay, so what this shows is that we set the world builder file, and we set it to this world builder file, which is in this directory. We both use the world builder for the model name, for the initial temperature model, and for the initial compositional model. In this case, we'll generate 5 compositional fields, because that's what we're actually going to use later on. And these are just, so we're going to output it in this directory, which is the directory which actually loaded. And for every parameter file, I already updated it to output to the right directory, so you can actually use it. One thing which will change a little bit over the course of this tutorial is the initial global refinement. I set it now to 2, and that's fine. But if you want to have more detail, especially when we're going to look at subduction zones, you might want to set this to 3. And I think sometimes it will already be set to 3. It's refined based on the compositions, as you can see in this model. So all the compositions except for the mantle will refine. And in this case, we're using 3 dimensions, and the rest and the box extents are 2000 by 1000 by 500. And I tried to make it a little bit more square. The rest of the parameters are just to make sure that it runs as quickly as possible. So now let's take a look at this model. And this is actually not what we want. We don't want to have an oceanic plate which is 500 kilometers deep. And so this is the compositional field, which you see where 0 is not present and 1 is present. And this is temperature field. We defined temperature field of this oceanic plate to be a constant, which is 293. And this is just the background still. So let's go and change that. So you should now see my slides again. This is what we just saw in the model. And this is just the same model we had before. I just spaced it out a little bit different. So we have our oceanic plate, we have coordinates, and what we're going to change is this model. And we're not yet. We're going to actually what we're going to change. We're going to add some maximum depth, because by default, the minimum depth for every feature is 0, and the maximum depth is infinite. So we're going to limit that a little bit. And we do that by just defining a maximum depth. And maximum depth is just 100 kilometers. And to make it a little bit more interesting, we're actually going to set the maximum depth of the temperature part to 50 kilometers. And again, you can run it with the same command, but then now using rvm3 overriding plate, depth PRM, and you can view it with the same in the same way if you want to. But I'm not going to do that for now. I just want you to, this is what it will look like. And I just want you to notice that now we actually have a reasonable depth for the compositional plate. And just to going back, we didn't define a maximum depth for the compositional models, but we did do a global one. So the global one caps off everything below it. And for the temperature, we actually defined 50 kilometers, and you can actually see that this depth for the temperature is less than what we have here for the composition. So that worked as well. Okay, so again, this is what we had last time. This just spaced a little bit differently. So this model we had, it's already starting to get something, but the temperature in here is not really interesting. And so let's start and make it a little bit more interesting. So this is the line we're actually going to change. We're going to give it a more interesting temperature model. And the temperature model we're going to use is the oceanic plate. Or sorry, the plate model. And that plate model is a model which is a lot used as a proxy for how an oceanic plate, the temperature distribution goes away from the ridge. So what we will need is a spreading velocity, and we'll need where the ridge is to be able to make a temperature model inside there. So that's what we do over here. We're actually also going to make it the maximum depth 100 kilometers, just because that's more realistic. We could also leave it out because it's already kept up by 100 kilometers. So the spreading velocity, we're going to set to 1 centimeter per year. So this is a unit meters per year. And we're going to use the ridge coordinates, which are these ridge coordinates, which is not that important. I will show you in a minute where they are. And again, you can run this with this command, and you will be able to, it will create a folder which you can view with this command like before. And that will look something like this. So actually we went one resolution higher, just to be able to see the oceanic plate a little bit more better. And you can actually, if you did this, you can actually turn off the grid, and that will actually allow you to view it more precisely. It allows you to better view the oceanic plate. And the reason so you see on the side, you see that there's an interesting temperature profile. So the ridge is over here somewhere, and you see the interesting temperature profile. But surface temperature is set ever the same. So in a minute, we'll solve that, and we'll actually be able to see where the ridge is in the model. But for now, just know that it's actually going along somewhere here, I think. Okay, so I think I'm gonna do one more addition before we have a break. And I think two small additions. Well, one big addition, one small addition. So the big addition is what we are actually going to add a second oceanic plate. And we now already know, so I rearranged this a little bit to make it a little more compact, but it's the same oceanic plate we had. So what we're going to do is we're going to add a second oceanic plate. So we start again with making an object. So we start and end with the curly braces over here and here. We give it a model name, which is oceanic plate. We give it a name, and in this case, we also give the maximum depth from the start. And we're going to define the coordinates. And the coordinates are going to be just this area. So that's what the coordinates define. Then we're going to do two more things to make it a little bit more interesting. First of all, we're going to give it even another temperature model. And this one is called linear. And we have to give that a maximum depth. And if you don't provide any parameters, what it will do is it will take the top temperature and it will take a bottom temperature based on adiabatic temperature, and it will linearly interpolate between those two temperatures. But if you want, you can also specify a top temperature and a bottom temperature. But we're not going to do that for now. The second thing we're going to do, and this is the first example of how these are actually, you can put multiple models in there, is we're going to put 2 compositional models in here. And so I said before, this is a list, so we can actually do that. We can put 2 objects in here, 2 compositional model objects, and both of them are just going to be a simple uniform. And the reason that this is useful is that we can play with the parameters maximum depth and minimum depth. And we're actually going to do that. So what we are going to do is we can have one model which defines a composition number 3. And we're going to set the maximum depth to 50. So that means that the depth of it will fill the composition with composition 3 from 0 to 50 kilometers. And the second model is also uniform, but instead it's going to fill it with composition 1. And it's going to do this from the minimum depth of 50 kilometers down to infinite. And it's capped off by this 100 kilometers anyway. And so this is the model we're actually going to run, or you can run. I don't think I have time to do it before the break for now. But you can run this with this command still here over here, and you can view it. I think I'm going to do it because it's going to be a new, instead of full, we're going to use mixed. So I will quickly show you how to do this in the virtual box. Okay, so I'm going to close Pair View. And let's also start using npr run minus mp2. For example, if you have 2 cores, or in my case, I actually have 4 available. And this is model 5 Atlantic.prm. And it may take a few seconds, depending on how quickly it is, how much cores you have. So again, we're going to open Pair View. And everything is going to be the same. We're just going to, so we're going to load the state, but we're just going to select a different state this time. We could still use the other state, but this state is going to be more interesting. So this is the PV view mixed C1T. I'm going to click OK. And again, use the second option, search files on the specified directory. And we're going to use directory 5, Atlantic. I'm going to click OK. I'm going to click OK. And this will load it for you. It may take a second, depending on how quick you're. And then you can just start and view the model. You can see. So what I did over here is in the solution, I used, for the bottom one, I used the threshold of temperatures, properties, between 300 and 1600 degrees Kelvin is being viewed, the rest is being cut off. And for the top one, I actually combined several plates, several compositions into one model. Okay, let's go back to the presentation. So this is what it's more or less, this is what it should look like. If you load in Pair View, we have the ridge over here. You can now see what direction it's going into. And we have well, I have a composition over here, which is the overriding plate. And we have 2 different compositions over here, which are each 50 kilometers thick. Okay, again, I just rearranged it a bit. So the only thing we're now going to do is add a different feature model, tectonic feature. And this one is called the mantle layer.
Menno, before you go there, we have a question in the chat, and that is, the mantle is at 1600 degrees, although we never set this anywhere. is this just a default value, or where does this 1600 degrees come from?
Oh, yes. That's a good question. This is, the default is some kind of adiabatic temperature. So it will start at 1600, and you can actually set where it starts, and you can set all the parameters you want for the adiabatic temperature in the global parameters. Or you could also, we'll see, what we're actually doing here, what we'll see later on, is you can, so I'll come back to that in just a minute. For now, we're going to add a mantle layer, and we're going to give it a name again. And because we added up to the top, the minimum depth doesn't really matter, but we're still going to give the minimum depth and the maximum depth, and going to give it coordinates. And the coordinates we're going to give it is just the whole box, because we want to have a background mantle everywhere. And in this case, we're only going to give it a compositional model, and we're going to give it uniform, and we're going to give it a composition of 4. So coming back to the background, if you don't do anything, it will give a kind of adiabatic temperature background from the start. If you don't put anything in the world border file. So the minimum world border file, I showed you the rvm1, minimum.wb, will return that there is no composition, but there is an adiabatic temperature in the background. And that's what's being overwritten by our models. In this case, we are fine with keeping that temperature in the background, so we're only going to overwrite the composition model. We're going to leave the temperature model alone. So we're going to leave the temperature as it is. And if you do that, it will actually won't look that much different, but you can actually, one exercise would be to see if you can visualize it inside ParaView yourself. Another exercise would actually world border would be, can you add a lower mantle and visualize it in this model? And with that, I would suggest we have a short break of, let's say, 10 minutes. So see you back at 1/4 unless there are any urgent questions. Or you can also just ask questions during the break.